Hello everyone, welcome back to the lecture. So now in this lecture we'll try to see one more problem and we'll try to see in which direction the beam has to be connected. So there's one more problem here. I'll not explain completely. I'll just give you an overall view of this. So here what is happening, the eccentricity is in both direction, right? If you observe it carefully, you see here the eccentricity is in both direction. That means your column is here, the center of the footing is here. So from here to here also there is eccentricity. This is a eccentricity in xx direction, and here also you have a eccentricity like this. So this is eccentricity in your yy direction. Okay, this is eccentricity along xx direction. This is eccentricity along yy direction. So from both the side there is eccentricity. So in this case your equation will become like this. That is p by a plus or minus mxx by zxx plus or minus myy by zyy. Here you have to find mxx and myy both. Here you can see, mxx is p into exx, myy is equal to p into eyy. I have done. So again, what is the load? Load is same. 500 kilonewton only is load. So when I'm saying xx, I have to take this particular distance. That is, I have taken 0.3. So this will be my 0.3. Yeah. So this is my xx. Okay. So this will be my, yeah, why it is xx? Yeah, p into xx is 0.3 and this is 0.7. Okay. Let me do one calculation. Wait. 500 into 0.7. Okay. It's coming 0.7 then. And how much is this? 500 into 0.8. Yeah, fine. It's okay. So this is your yy. Okay. This is ey direction and this is ex. This is the eccentricity. So here the calculation is mxx is equal to p into exx. P is 500. So 500 into 0.8 we have done. Okay, so this is your exx. Yeah, this is correct. See, your x axis is here. About that, you are supposed in a perpendicular direction, you have to take the eccentricity. Okay, so this is your 0.8. So this is your mxx what we have taken. 500 into 0.8, if you don't know, you'll get how much, 400 kilonewton meter you're getting. And myy. Yy means your yy direction is here. So your eccentricity will be this much. How much is this? So this much is given as 0.7. So this is 0.7. From the center of this to here, it is 0.7 that is mentioned here. Again, 500 into 0.7 you do, you'll get 350 kilonewton meter. Understood? How this 0.7 is coming, you already know that. So if this is 2 meter, half of this is 1 meter. If this is 1 meter, and if this column dimension is 0.4, half of that is 0.2. So 1 minus 0.2 will be 0.8. So this becomes 0.8 here. In the same way, here also it is 1.7. Half of 1.7 is how much? Half of 1.7 is 1.7 divided by 2 is 0.85. If this is 0.85 and if this is 0.3, half of this is how much? 0.15. No, if this is 0.85 minus this is 0.5. So if you do this, how much you're getting? 0.7. So that is why you can see, this distance what they have given from the center to this will be 0.7. So that is why we have taken here 0.7 for the calculation. Understood? No? Yeah, that's it. So when you do all the calculation like this, again you see the maximum pressure is coming 876 kilonewton per square meter, which is greater than your SBC, and your minimum pressure is minus 554, which is greater than 0. Which is less than 0. Again, both this is not safe. Again, what I'm basically trying to tell is, when you have a eccentricity in both the direction, your moment is going, your this thing, maximum pressure and minimum pressure is going way beyond. In the previous case, if you see, if I go in the previous case, here your eccentricity was in only one direction. So here what was happening, your maximum pressure somehow you were able to satisfy, but minimum pressure you were not able to satisfy. But since here eccentricity is in both the direction, you see your maximum pressure is 876, which is greater than SBC, and your minimum pressure is minus 554. So again, it is not able to satisfy. Okay, whenever you have whenever you have eccentricity in both direction, again you're at any cost you're not going to satisfy. Right? Now, what is the solution for that? Solution for that is you have to connect that with a beam. That is a solution for it. So we'll try to give you a small idea. Imagine if this is one footing, this is my another footing, and then I have another footing here. Okay, so these are the three footings what I have. And let us consider that here I have a I have a column here. So this column is having eccentricity in one direction. Here also I have a column. It's having eccentricity in one direction. Here there is no eccentricity. It's a concentric column. Now my point of discussion is this one. So now you tell me for this particular, I'll remove that, not required. Yeah. Now you tell me for this particular column, okay, or for this particular footing, in which direction I need to connect the beam. See, it's eccentric only. Okay, it's eccentric because your footing CG is here, column CG will come here, but so it's not matching. So it has become an eccentric column, eccentric footing. But what is the advantage? Here the eccentricity is only in one direction. That means if this is my XX direction, I'll draw it here. So if this is my XX direction, and if this is my YY direction, so where is the eccentricity happening? So if this is my XX direction, I'll write X and X. And if this is my YY, so where is the eccentricity happening? So eccentricity is only in your XX direction, right? Why XX direction? Because you see here, the footing CG is here. The footing CG is here. The column CG is here. Okay, right? So because of that, you see XX axis is here for the footing, column XX axis will be here, whereas YY axis for the footing is here, column Y axis is matching. This is matching, this is not matching. That means your eccentricity is in this direction. Yeah, eccentricity is in this direction. Okay, so your eccentricity is along XX direction. Now you tell me in which direction you are going to give a beam. So the beam will be given in which direction? Perpendicular to the eccentricity you're supposed to give. That means how I'm supposed to give it, like, say I need to connect this particular thing. I need to connect this particular column with this particular beam in this direction. Okay, so that is a logic behind that. I'll do it once again. So I'll be connecting this column with this particular, I'll connecting this beam with this particular column in this particular direction. Okay, why is that so? It's very simple. You need to understand. Say the eccentricity is in this direction. Okay, eccentricity is in this direction. So your P load is coming here. I'll make it little darker. Yeah. So your P load is coming here. And this is the eccentricity. Because of this, the moment is coming in this direction. Getting the moment is coming in this direction. Okay. So this moment, who can take this particular beam can take. Like for example, imagine like this, that your moment is coming like this. From here, your moment is coming. This is your column. And because of the eccentricity, the moment is coming like this. So if I'm giving a beam like this, so let me 1 minute. I'm just searching for a scale. Okay, I did not get the scale. Let me do it like this. Huh, I have this. I'll do it like this. Yeah. So if this is your column, if this was a column, and because of it, there's a moment getting, if I connect that with a beam in this direction, see this moment is coming like this. So you have enough depth of the beam. So this particular depth can take your bending. If this is my beam, and if moment is coming like this, so what is happened? Whatever moment is coming, no, this depth of the beam, okay, is able to resist that moment. Okay. Suppose your question may come, sir, what will happen if you, instead of connecting this here, you give one more beam from, instead of giving this beam, what will happen if I give a beam in this direction? So if you're giving a beam in this direction, I'll tell you what will happen. See, the moment is coming like this. Okay, I gave a beam in this direction, that is this particular beam. Here I gave this one, this particular beam. So because there's a moment coming in this direction, I've given a beam, it will resist your bending. Okay, but if I give a beam in this direction, okay, so that means this particular thing I'm showing it like, if I give a beam in this direction, your moment is coming like this. Okay, so now your beam is in this direction. So what is happening? If you're giving a beam in this direction, this particular moment is trying to twist. So it's a twisting moment. What is not trying, it's not able to take your bending. Your moment is like this. But for this beam, if you're putting a beam in this direction, this moment what is getting created, no, it will create a twisting moment. It's a twisting moment, right? So your this beam is of no much importance to you, because the problem is, because of the moment, this additional moment has to be taken. So who is going to take? The depth of the beam should take. I mean, the beam has to take. So if I'm going to, if this is a bending and if I have this much depth, no, this beam has to take. So what is happening? Whatever moment is coming, no, this moment is coming like this. But for this beam, if you're putting a beam in this direction, this moment is coming like this. So your this beam is of no much importance to you, because the problem is, because of the moment, this additional moment has to be taken. So who is going to take? The depth of the beam should take. I mean, the beam has to take. So if I'm going to, if this is a bending and if I have this much depth, no, that bending can be taken, that moment can be taken. But if I provide it in this direction, that particular moment is creating a twisting moment here for this particular beam. So that is why this particular beam is more effective compared to this particular beam. That's it. So you may ask, by providing this beam, will it not help? It will help you. It will help you. But this particular beam will help you more in comparison to this particular beam, because for this particular beam, if you see, it is able to take the bending. So how the bending will be taken? So you have to design your beam for that. Whatever is the moment coming for that particular moment, you have to design your beam. Usually, whatever is the depth of the footing, no, that much will be the depth of your beam. For example, let us say the footing depth is something 500. So you'll be providing a beam of, let us say, 300 by 500. 300 is the width of your beam. Depth of the beam is 500. You have to do the calculation for that. Again, you can make use of softwares like Safe and Safe software, or you can have your own Excel sheet, or you can use Safe software, and you can do the designing of this thing. Okay, you're getting my point, no? So this is how it has to be understood. Now, let me ask you one more question. Yeah. Now I'll draw one more thing here. I'll draw one more footing here, and this time let me make this column to be eccentric in both direction. Here I'm connecting this with this particular. Yeah, I have a column here. Okay, and I think this I need to shift a bit so that I can match this thing. I'll shift it here, and this column also I'll shift somewhere like this. Okay, I mean, I cannot do that exactly, but it's okay. Leave it. Let me do that. Let it be here only. No problem. Yeah. Now you tell me in which direction you are going to give a beam for this. For this particular, now here you see the eccentricity is in both direction. Along the x also you have eccentricity, along y also you have eccentricity. In that case, you need to connect this with the beam in both the direction. From this column to this column, you connect a beam. From here to here, you have to connect the beam. Here also you're supposed to connect that with the beam. Okay, I mean, it has to, I have to take it little this side. Yeah, and this I'll increase. So you have to connect that beam in this direction. Understood? You getting my point? No. Whenever you have a eccentricity in both the direction, you need to give beam in both the direction. Whenever you have a eccentricity in only one direction, okay, what you need to do is you have to give opposite to that. When I say opposite to that, or if you want to make it very clear, if you don't want to fall in all this understanding and all, what you can do, wherever in whichever direction there is no eccentricity, no, parallel to that you have to give a beam. For example, let me do it here. Okay, let me go with a different image. This is not required. I'll draw one more image and I'll show you. Yeah. So if this is one footing, and then I have one footing, then there is one column here. This is another footing. Okay. Then there is another column here. There's another footing, and I'll draw one column here. Okay, fine. So in which direction you are supposed to give a beam for this particular footing? Whether you should give a beam in this direction or beam in this direction. Very simple. Just see through which axis there is no eccentricity. Along x-axis there is eccentricity, but along y-axis there is no eccentricity, right? So wherever there is no eccentricity, no, in that direction you connect that with the beam. That's it. Because there is no eccentricity here, you connect your beam like this. That's it. Very simple. Understood? Understood the concept? Fine. Yeah. So this was all about the eccentric footing and all. So I hope you have got a complete idea, like when to see beam at any cost you have to provide. We have seen that if you don't provide a beam, that means there will be a failure in your footing. Okay. You have to connect the beam, and how the beam will be designed. For that, you have to use software like Safe, and from there you have to check how much moment it is able to resist. Based on that, we can give a beam. But normally, usually how to design it. Sometimes if you don't design it, if it is a small structure, whatever is the depth of the footing, that much will be your depth of your beam, and width you can take somewhere close to 300 mm, and then you provide a 16 diameter 3 bar at the top, 16 diameter 3 bar in the bottom, and you provide a 8 mm stirrup at 150 center to center. That is sufficient. Again, this is not what you're supposed to do. You have to do the designing and you have to check. But in worst case, because lot of construction wherever it is happening, people don't give a beam, they just give a footing, and you already seen through the calculation, without giving a beam, your footing is not going to be safe. So in that case, what you do, you just connect that with the beam. And how to connect a beam, I've given you an idea. Now I'll take you to the same thing which has been explained here. Now you see, for this particular column, whether the beam what they have given is correct or not. Just try to apply your logic. First you find x-axis. So this is your eccentricity in x-x direction. This is your eccentricity in y-y direction. For this particular footing, tell me where is your eccentricity happening, whether it is in x-x direction or y-y direction. Okay. Where the eccentricity is happening? See here. This is the center of the footing and center of the column here, right? See. Wait, let me do like this. Your footing center is here and column center is here, right? So that means along the x-axis is matching. Along the x-axis it is passing. So wherever it is passing, no, there only you connect the beam. That is why the beam has been connected in this direction. Understood? In the same way, come here. Tell me now, along which axis there is eccentricity? Along x-axis or y-axis? Along y-axis, along x-axis there is eccentricity, isn't it? Because if this is a footing of, wait. So if this is my x-axis and this is my y-axis, okay? So along which axis there is eccentricity? Obviously the eccentricity is in x-x direction. No, why? Because your footing CG is here and your column CG is here. So eccentricity is like this way. So in which direction there is no eccentricity? In y direction there is no eccentricity. Why? Because footing CG is here, column CG is also. So in which direction there is no eccentricity, you provide a beam parallel to that. That means in this direction I'm supposed to provide a beam like this. Understood? So this is a logic behind providing the strap beam. Few people call it as a strap beam, few people call it as a tie beam. So it is specially given in the eccentric footing. Same here also, you see, here also there is a beam connected. Here also there is a beam connected. Here also there is a beam connected. So everywhere you see, wherever you have eccentric, no, eccentric columns or eccentric footings, you have to provide the beams. So you know in which direction this beam has to be created, connected. See here, here he has given that in this direction. Why? Again, for a very same reason. See, where is the eccentricity happening? See, this is my x-axis and this is my y-axis. Okay, so the eccentricity is coming in y-y. In x-x, you see, it is there is no eccentricity in x-x. So in the x-axis, there is no eccentricity because your footing CG is here and column CG is also matching. Okay, only the y-axis is eccentricity. Because of that, they have given a beam in this particular direction. Understood? No? So this is how you are supposed to understand the concept, and based on that, all these footings are designed. And then for the same drawing, they have given the beams. You see here, they have given the length of the footing and the breadth of the footing and the depth of the footing. The reinforcement is given. You see the beam details. You're supposed to provide a 9-inch by 18-inch. Why it is 18-inch? You see, whatever is the depth of the footing, no, same depth they have given in the beam. Usually that is what we try to do. You see 18, 18, 18. Here also 18, 18. 18, 18, 18, 18 they have given. So whatever is the depth of the beam, whatever is the depth of the footing, same will be a beam depth. And then 9-inch or a 12-inch you can provide. 9-inch is also sufficient. 12-inch is also okay. 15-inch they have given it here. You see the reinforcement. Bottom they have provided 20 diameter 3 bar. Top they have provided 16 diameter 3 bar. And they have provided 10 diameter bar at 4 inches center to center. That is your stirrup. So this is a typical cross section of your strap beam. See here. So it's a beam what you are given here. This is your top bar 16 dia 3. Bottom bar is 16. Bottom bar is yeah. Sorry, bottom bar is given here. Where is bottom bar? It's written here. See, 16 dia 3 bar at the top. Bottom is 20 diameter 3 bar. You're supposed to provide a 2-leg stirrup of 10 diameter at 4 inches center to center spacing. Understood, no? So this is how the entire eccentric footing is designed. If you want, I'll show you one eccentric footing also. You can see the reinforcement of the eccentric footing. This can be one good image. Is that gone? Oh, it's not visible. Okay. Okay, there's one image at the beginning. I'll show you that only. Where is that? somewhere here. Yeah, you can see the beam here. This is that beam, okay, which has been connected. So you'll be providing a top 16 dietary bar, let us say bottom 20 dietary bar, and then you're going to provide a stirrup like this. Understood? No? So this is how the eccentric footings are designed. I have explained you the entire concept behind the eccentric footings and all. Yeah. So I hope you have got a better idea about what is eccentric footing, what is the reason behind providing eccentric footing, why the beam has to be provided. Beam is provided to take care of the moment, and which direction the beam has to be provided. All those things we have understood. So I will see you back in the next lecture. Thank you.